Howdy, everybody. We are here for the last day of Advent of Code, at least ones that I have planned. We're going to talk about day 25, and we're going to implement the Stoer-Wagner algorithm just to see how it works. And, we'll be doing it in Rust, so we'll have like an idea of what it looks like and how it works and why it works. That's kind of what I'm hoping everyone will get out of this. And it will be in Rust, right? So we can actually see it in Rust. If you remember from my previous day 25, I just did it in Python and I used Network X, but I'd kind of promised we'd talk more about, in particular, Stoer-Wagner. The other solution was to do max flow to get the min cuts, which we talked about last time. That might be fun to implement in Rust too, so I have that on my list of things that might be interesting. But like I think in general, we'll be able to move on to other stuff as we get to this point. So, as we finish up this video, we can kind of broaden our scope and talk about any other problems or any other things that might be interesting and whatnot. So, with that, let's get into the problem. So if you remember, day 25 is Snowverland, and essentially you have a giant wiring diagram and 4 different components, right? They're all wired to each other, and it turns out it's using too much energy, and you want to like cut the energy in half, and it tells you there's like exactly 3 places that you can perform the cut, and if you cut those 3 wires, then it will like split it in half, right? Or generally split it in half such that you have like the way to think about it is you'll partition the graph into two separate distinct sections, and that's what they want you to do. So Stoer-Wagner was designed to solve this problem. It's not the most efficient, and like I said, there's other ways to do this, like the max flow is essentially solving for the min cut. And so you could do it that way. You just have to kind of test back and forth, like, what are my sources and sinks there? But today I wanted to focus on Stoer-Wagner and the intuition of what it looks like. So if you spit out the diagram, it looks like this. And you can see fairly well, right? It's like there's clearly 2 parts to the graph. There's this side and this side. And so cutting these 3 wires right here would make a bipartite graph, is what they call it, right? Like 2 distinct parts of the graph that are all interconnected with each other, but don't connect to the other part of the graph, right? So there's a clear group over here, a clear group over here. You're partitioning the graph into two pieces, right? So what is the Stoer-Wagner algorithm and why does it work? Here's the paper. And I actually tried to refer to it or implement it as they designed it, so it will look a little bit like that, the way they designed it, except for the end of like coming up with like the partitioning of it and what the partition looks like at the end, and we'll talk about that in a second. But you can see here though that they go into a lot of math. I'll try not to talk a lot about the math of it. But they actually have an example, and we'll go over the example and see how it works. But I want to talk about, there's also the Wikipedia article, which I'll link. And most of it, except for the example code down here, just comes straight from the paper. So if you want to read the paper directly and you understand enough math, it's not a lot of math, but if you understand like what these type of things are saying, they do a pretty good job of describing it. But I guess what I should say is I feel like the paper is actually approachable if you've read a paper or 2 before and you kind of understand, big O notation and stuff like that. My guess is you could read this paper without much issue. So it is approachable. The Wikipedia article has maybe some introductions that might help you understand it better, but give it a try. See if you can't read this and understand what they're doing. But what is the intuition that makes Stoer-Wagner work? And in general, what Stoer-Wagner doing is node contraction. The idea is it's going to slowly like take nodes and join them together, and then, you know, create new links between the nodes based on concatenating them together. And the intuition is the place where you want to partition the graph, like where you'll get to the point where you want to cut these three, is you're much more likely when you're over here to be combining these nodes. Not much more likely, you are more likely to be combining these nodes than you are to be combining like this node with this node when you're doing node contraction. If you're doing node contraction for the most likely connected or the most tightly connected nodes, right? And that's the key to the algorithm. If you're able to say like you're considering this node, like what are the most tightly connected? It's the ones like closest to it, right? But then if you start considering this node, if you consider this node and this node, you start seeing like, oh, these two are like more tightly connected to like, say, this one or this one, because they both kind of like come from this thing. So when you're thinking about like connectivity of the graph, this half over here is like more tightly connected to this half of the graph than this half of the graph, right? And so you're more likely to like consider these tightly connected nodes. And if you continually do that, you slowly get to a point where this side connects to itself and this side connects to itself, and that tightly connectedness will bring forward these three lines right here, these three connections, right? Because these are more tightly connected and these are more tightly connected. These are likely or will, at when you do this node contraction, contract with each other before they contract over to here. So that probably wasn't a great explanation. I think, though, it will make more sense if we actually do it in an example. And so that's why I have this right here. The way the algorithm works to find that tightly connectedness is you do what's called this minimum cut phase. And the way they describe it, it's the same here as in the PDF. The way they describe it is they say you're going to slowly add nodes to some new set A until you've added all the nodes. And the last two nodes left are considered your like cut of the phase. So the last two that you add to this thing are considered like the ones that you want to cut. So then the question is like, well, how do you get the first one and how do you add the rest? That's where they get you start with just a random one for the first one, but then you slowly add to A, the most tightly connected vertex. And so what are they saying there is the vertexes that are most closely associated with it. So if I'm considering if A is in my set, I want to consider which ones are most tightly connected to it. What are they saying by that? They're saying, this one has a distance of 2 and this one has a distance of 3 to it. So I want to add the third one. Oh, if I didn't mention that before, the algorithm is an undirected but weighted graph. And so when we go to solve our problem, we don't have weights here. We'll just give them all a default weight of 1. But it's meant to be on a weighted graph, and you'll see why that's important for the tightly connectedness, right? So obviously E is more tightly connected than B to A. So you would add E first to that set when you're coming in here. Now they actually tell you how to implement this in the thing. If you go down to the running time section, they say the key to implementing a phase efficiently is to make it easy to select the next vertex to be added to the set A, right? So what they're saying is, what's the most efficient way of, like, let's say you've added these 3 to the set, like what are the most tightly connected? Well, your candidates are here and here. How do you efficiently keep track of that and choose which one is next. And they say the way to do that is all the vertices that are not in A should reside in a priority queue based on a key field. And what they basically say is use a priority queue. And every time you add a vertex, you should update the weights of the edges of that vertex, right? So, and if you continually do that, you will maintain, the priority queue will help you maintain a list of the most tightly connected nodes. And what does that mean? So why does that work in the priority queue? Imagine we're starting at B, and we want to find the most tightly connected nodes from B, right? So maybe we start here and start here and start here. So we have E, F, and C as candidates, and this one is a 3, right? And these two are 2s. You're going to want to go this way. This maybe this is not going to end up being a good example, but now what you want to do is add these other two to your queue, right? So you have D and G, and so like, what are the priorities of D and G? Well, they're 4 and 2. If you ever get in a case where like you've seen one before, like say we're at G and we want to add some values and we've already seen F because we've gone here, we're going to increment F's by 1 to get it to there, and maybe we increment H's by 3, right? So you're going to be adding these nodes of what has already been seen, I guess is the way to describe it. And that's why the priority queue works, is in the tightly connected, because you're wanting to consider all of the nodes that you've already added and how tightly connected they are to the other nodes that have not yet been added, right? And so if you do that in a priority queue, it will help you like determine which of the ones you should go to next. Okay, well, I think the example will help if we actually just walk through it. But essentially, you're going to do this minimum cut phase over and over until you've contracted the entire graph. So once you do the minimum cut phase, you'll have those last two vertices, S and T is what they call it, and you're going to merge those two nodes, do a contraction of those two nodes in the graph, and kind of track the minimum and those two values. And then once you've done that all the way, the minimum cut, the lowest value of the weight that you did, which what you'll see again in a second, turns out to be the minimum cut. And again, the reason for that is these nodes are more likely to contract over here, and these nodes are more likely to contract over here. And eventually, the only way that like these three will ever contract is if all of this side has contracted. And so once all of this side has contracted, then you will get this one where you contract this one at some point in time, right? And its value will be 3, whereas these will all have been larger contractions, and that will give you the minimum cut. So I think an example will just kind of help you understand how this works. So I'm going to do a lot of drawing on here, and I apologize for my handwriting up front. But let's just do that phase iteratively over and over again to show you what it looks like. And we're going to track the cut value, right? What was the weight in the priority queue? And then we're also going to track what nodes we contracted, those S and T values, right? And I'm just always going to start at B. The paper always starts at this B position, but it will still work if you just pick any random node. In fact, the priority queue, they all start at 0, so technically pick any node that's a 0, but we'll just always start at B so you can kind of get an idea of how it works. Okay, so what does the algorithm do? First, we add B to the set, and then we want to add all of its neighbors, update the priority queues to all of its neighbors, right? So we have a 2 to A, a 2 to E, a 2 to F, and a 3 to C. So 3 is obviously the largest of those, so we'll add C to our list. So now we have B and C in our our set. but we want to add C's nodes to it, right? Or C's edges, update C's edges. So we'll has a value of 2 and D has a value of 4, right? So now we've got a bunch of 2's and then a 4. 4 is the highest, so we'll go to the 4 one, which is D. So we want to add D's to the thing, right? So now we have 2 here, but we already added 2 to this one. So it's actually G is going to be the highest. It now has a 4. And then we got a bunch of 2's right here, right? So we'll add G, and now we want to add its ones. So we have a 3 here, and we have going 1 this way to F. But we already added F when we did this. So F now has a priority of 3. H has a priority of 3. And these two have a priority of 2, right? So we'll go this way because they're both assigned priority. It doesn't matter. So we add this one, and that doesn't actually add any edges because we've already done those. But now you can see, like, as we've done the priority, we've kind of like used all of these nodes over here. So the ones that are left are 2, 2, and this one has a priority of 3 because it was added from B and G. So we have 2, 2, and 3. I should say 2, 2, and 3 right here. So we'll add F to our set, right? And now we need to consult those. So we add E. So we add this line right here, which makes this a priority of 5 because we've already seen it from here, right? We've already seen E from here. So now E has a priority of 5 and A has a priority of 2, right? So we want to add E to, we'll do E. And then now E has a priority, or we add A to the list with a priority of 5 again. And A and E are the last two that we consult, right? So E is our S and A is our T. Those are going to be our cut values, and the cut value is the priority at the end there. And right, A's priority was 2 and 3. So if we track those, we get the cut, or the contraction, is going to be on E and A, and it has a priority or a weight of 5. So we'll just track these variables right here on this side. Okay, so that's the algorithm for the min cut, right? Again, you're essentially using a priority queue. You're picking the one with the highest priority, and once you do that, you're adding its nodes, right? So when we were over here and we want to add its edges. G was already there because we had seen it at 2, but it now we want to increment its priority by 2, so G now has a priority of 4. And you're just going to slowly do that until you traverse the whole graph. And once you've done that, the last 2 that you do are the ones you're going to track for its weight and the cut set, right? So now we actually want to perform the contraction, right? And so the contraction is E to A. So we want to move A down into E. And the way to think about this is we're going to put A down here and get rid of A. And so the way that we do that is we want to update all the nodes that are connected to A and now have them connect to E. But where there's already a connection, instead of just adding them, we want to like update the values, right? So you can see B is connected to both of them. And so we're going to change this from a 2 to a 4. It's the sum of these two weights right here. And then we can remove this and remove, obviously this one isn't helpful, so we remove that one. So what we've done is we've removed this part of the graph. You can remove this node during the contraction. And so now we have a weight of 4 going from B to E, where E contains A, right? And we've removed that. And we're just going to do that over and over again, right? So I'm going to go a little bit faster each time we go through this, but the idea is we're going to be doing that same thing, right? So let's start at B again, and we'll add its weights. We have 2, 3, and 4. So we know we're going this way, right? And now we have 3, 2, and we go this way, and so we add this one to the thing. which makes this a 5, right? So now we have 3 and 5, right? So we're going to go this way, and so we're going to add this one. So now we have a 3 and a 1. So we're going to go up here with this one's the highest priority. So we're going to add this one and this one. So this gives us a 4 and a 3 down here, right? Because it's this plus this. So we're going to go here. That's the highest, 4. And now we're going to add these ones here and here. And this one is now a 2, 3, 4, 5. So this is a 5 and this is a 2. So we're going to go down here. So now we're going to move this way, which is a 3, but it's already has one there. So this was a 2 before because of this one. So this one's now a 5. So we go here and now we're done, right? So the last two we did were G and H. So those are our S's and T's. And the weight to go from there was, again, 2 plus 3 is 5. So our weight was 5. Now we need to do the contraction. So we're going to move H into G, right? So we won't need these anymore. But again, D is connected to both of them. So the new weight over here is the sum of their weights, right? So now you have H in here as well, is a way to think about it. And now you've kind of removed this node from the graph. Okay, let's keep doing it. So now we have, we're going to start back at B again. We've got 4, 2, 3. We've seen that before. We're going to go this way and add this one. So now this one has a weight of 5 and this one has a weight of 3. So we're going to go down here and add this to over here. And we have a 3 and a 1. So we're going to go back up here and we're going to add these two. And so we have a 4 and a 3. We're going to go down here and this is going to be, we're going to add this one to the node. And that's actually going to be the last of it, right? So is that the last of it? Yeah, we went da, 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 and then da. So yeah, that is the last. So we have G and D that we're contracting, right? G and D. And what was the weight again when we added, when we went from G to D? It was 7, right? 1, 3, 4, 4, 5, 6, 7. Oh, we're actually going D to G. Sorry, that's I did that wrong. So you're going to go here and then here, and this is a 3, this is a 1, and then you get a 3 and a 4, and then you go from here to here, which is 4 plus 2 plus 1 is 7. So it's D to G with a weight of 7, right? Again, the priorities are adding, right? So it's when we added G to the set, it first was a 1, but we went up here and added G to the set, updated the priority to a 3 for this one. But we still went this way because this was a priority of 4, and then we went down this way. So it was 4 plus 2 plus 1 is 7 was the cut. And we want to merge D into G now. So now D is going to be over here, and we need to update the weights, right? So these two were connected. So this is now a 6, and then we're going to remove this and this and this. And now you can see like we've removed this part of the graph right here, right? This part is gone. And now we're just going to do the algorithm again, right? So we've got 4, 2, 3. We've seen that before. We go down this way. And now we've got 5 and 3. When we go down we go down here, right? And so now we have 1 and 3. So we do this one. And so that gives, so we go to here, and so now we have 6 and 1, which is actually 7, right? 6 and 1, 7, and these are the last two, C and G, right? C and G, and it has a weight of 7, right? Because it was added here. Its priority, G's priority, was updated here and then updated here. So now we want to merge these two, right? We're going to merge G into C. And this is the case where, notice most of these have been simple and we've just been updating it. this is where we add a new connection, right? C and F are not connected. So we need to add a connection here, and it has a value of 1, which is this right here. And then this will go away, and these will move up here. So we have H, D, and G. We'll remove these, remove this one. And so now you can see our graph is just these 4 nodes. We've contracted these 4 nodes. But okay, let's keep moving. So again, we've seen this before, 4, 2, and 3. We're going to go this way. So we go this way and we add this one. So now we have a 5 and a 3. So we're going to go down here. And so we have now I want to add this one to this one. So we have a 3 and a 1 going to it. So this is a 4. And that's actually it, right? So now we're going to contract this node with a value of 4. And so that is, sorry, which 2 was it? It was, we're going to contract this node with this node. So C to F. Okay, so let's do that. So we're going to move all these down here, H, D, G, and C. And we want to contract these nodes. This gives this a value of 5. And we'll get rid of this node, and now we get rid of this node and this node, right? And so now we only have these 3 left. And we'll do this. We got a 4 and a 5. So we'll go down the 5 first, and then we'll add this one, which will be a 7, right? So 4 plus 3 is 7. And our contraction now is this one and this one with a value of 7. So we're going to do F and E with a value of 7, and we contract those 2 nodes. So this becomes a 9, and all these will go over here, H, D, C, G, and F. And we'll remove that, remove that, remove that. And now we've just got this last contraction of 9. These are the last 2. So this is a 9 with a B and an E. The B and E is what we do the contraction on, right? And that's the algorithm. So now you've done all these minimum cuts, right? That's all of the minimum cut phases, I should say, right? We've done this minimum cut phase. And then what does it say? How do we know what the minimum cut is? If the cut of the phase is lighter than the current minimum, then store the minimum cut. This is just a fancy way of saying whichever one of these weights was the smallest is the cut where the minimum cut happened. And so it's saying that this cut right here that you performed is the minimum cut, and it is the centrality of the thing. And so remember, what was that cut? We had merged all of these nodes over here into a single node, and then we performed the cut on these 2 nodes right here, right? So these 2 nodes are the cut. What is that telling you? That is the smallest cut, right? Or that is the minimum cut. Again, I hope the intuition, now that you've seen the algorithm work, I hope the intuition makes sense. Like wherever you're starting from or however you're doing it, you're slowly contracting all the nodes on each side of the partition. And eventually you're going to do a cut that's going to be the smallest one, and that's going to be where like the minimum cut is, right? So the way the algorithm works is you're either going to contract this side, or you're going to do it in some pieces. Like if we go back to the original example, our first cut was actually over here, right? But then we spent a bunch of time over here contracting this graph. Eventually they're going to contract, right? All the way, all of the sides are going to contract, and then you'll get that, right? And that's the intuition behind why it works. So they do a bunch of math and lemmas and theorems and stuff to like help prove that. But that's the general intuition, is slowly these nodes are going to converge, and these nodes are going to converge. And they'll contract into a single node where you'll perform a cut right here against the other side, and that will be the minimum cut. And it actually, when you're running it quote unquote randomly, like with pick a random value from a priority queue, sometimes it'll be longer to find it. When I say longer, what I mean is to find that minimum cut, like to find this one right here, but you actually won't know it's the minimum until you've contracted the whole graph, right? There's a potential for you to have to contract all these nodes and all these nodes, and then all that's left is contracting this one, and that's the minimum cut. But that's what will help you find that cut, right? You will eventually find that minimum cut between the two. And that's the algorithm, right? So the way to think about it is, if you're looking at this graph, you're slowly merging all the values. Oh, I think you're slowly merging all these nodes over here and these nodes over here, and eventually these will all become one node, and you'll try and merge it over into here, and it will require you to cut these three, and this will be the smallest of those cuts, right? And again, because when you're during that cut phase, you're doing the most tightly connected. Like, what it's saying is these three nodes right here, another way to think about it is these three nodes, or these three links, are like least tightly connected to the nodes on this side and the nodes on this side. So when these actually get cut, you will have done the whole partition on one of the sides, and that's your answer. So there's two ways to, like, now that you know that that's the minimum cut, right? Obviously we know that the minimum cut is for this graph is 4, and the cut happened when you merged C and F, when you did the contraction of C and F. But how do you like reproduce it and say, oh, well, what are the values? Well, if you remember, I was kind of tracking them as we were merging them, right? And you eventually got to a stage where you had G, D, and H up here. I guess I can do that right here. If you had G, D, and H up here, if you were tracking all of those values, you could do that. It's a little bit hard to track those, though, especially you don't know the size of the graph. And so that's one way to track them. And then if you had tracked all of those in the algorithm, like let's say we were tracking, that all of these values were whatever, on this side of C, it was at this point in time, if you were tracking that C included G, D, and H, then you would have your partition, right? You have your partition right here. But if you look at most implementations, what they actually do is they say, well, how do I say this? I don't want to track all those values, those merging of the nodes, because it can become a lot, right? Imagine you're doing all these cuts, you're tracking all those changes and values, you end up storing a lot of data, is the way to think about it. Instead, what you can do is just recreate the partitioned graph using a breadth first search. And how do you do that? Well, you know the contractions you've done up until this point, right? All of these are the contractions you did up until this point. And so these contractions actually create another graph, right? And once you create that graph, you can then do a breadth first search, and that will give you the partition. So I just want to show you what that looks like really quick, right? So let's recreate. This is the original graph. Let's create a new graph from these phases of the min cut, and from there we can determine. I'll show you how we can actually figure out it was these four, right? So our first cut was E to A, right? So we add E and A, and we create some links between them, and then we had G and H. So we'll add those, and then we had D to G, right? So we'll add D links to G, and then we had C to G. So we'll add that one right there. And then from there, that's it, right? So these were all the links up to our minimum cut phase. And then we know that C was the value we were looking for in it. So if we do, this is now our new graph. You can think about it as like, these are the graphs of the links that were made, the joins that were made when we did the contraction. We just have to iterate over these four, right? We have to say like, okay, so what does the graph look like? Well, if we do a breadth first search, it includes C, D, G, and H. And like these are the connections that you need to get there. If that or these are the contractions that happened during that partitioning, and so these would be the values you include. Notice E and A is in the graph, but it's not connected, so this one wouldn't be seen in the partition. And this is, so again, this is how you would get to, this is the partition of the graph. The minimum cut was, so the min cut was 4, right? Because it was this cut right here that we performed. And then the partition is going to be C, D, G, and H. Like this is the partition of one side. And then it's really easy for you to, what is the other side? It's just the graph minus these values right here, right? And so that allows you to get the two partitions, the bipartite graph that's generated. Okay, that example, hopefully that helped you understand the intuition. And I'll just say it one more time. The intuition and what makes the algorithm so cool is the node contraction causes all of these values to, causes these nodes right here to slowly merge, and these nodes slowly right here merge, and they will do it preferentially because these ones are more tightly connected than these ones. And so whenever you're contracting on this side, you're always going to contract these nodes to each other. And whenever you're contracting on this side, you're going to contract these nodes to each other. And eventually you'll get to a contraction that will contract, like all of these will be combined as one. You'll contract it into another one of these, and it will produce this. And that will be the minimum cut for the thing, right? Again, give the paper a try. It's kind of cool to read and understand how it works, and they do a lot of detail. I think they explain it pretty well, and it actually works. So let's look at it in code. First of all, I would like to thank, let's see, who was it that found it? Adam Glass 2599. So I had mentioned before when I was doing the original video, I didn't know, I wasn't familiar with any like Rust version of Stoer-Wagner, and Adam Glass 2599 pointed out that RustWorks core will actually do it. RustWorks is like a Python library that's meant to replace NetworkX, but it uses Rust as like the core of it. And they've actually made their algorithms available, obviously, in Rust, so you can use it in Rust, the stuff that they have. They don't have all the things that are available in NetworkX, and so that's something I thought would be interesting, maybe adding some of those missing features to RustWorks. So if you're interested in doing that, or I may show you in a couple videos of me trying to do some of that stuff, we'll give that a shot and see how it works. But you can actually see, you can use their implementation of Stoer-Wagner to get the min cut, and I'll show you how it works. You just have to build their graph right here, which is an undirected graph, and then you can run Stoer-Wagner on it. But I want to do it myself, so I actually have the example here that comes from the Stoer-Wagner paper. I'm going to create a graph, and then we'll actually we'll use it to solve that graph, and then we'll actually use it to solve the input for the problem, right? And if you remember, once you do the cut, once you do the partition, they want you to return the two sizes of the partition multiplied to each other, right? And so that will give you the answer to part one, but we'll get back to that in a second. So how do we implement Stoer-Wagner in general? Well, I'm going to create a graph, and I thought because we're doing a lot of work in the algorithm, it would be good to have an actual graph that I could create like some methods against to simplify like the graph interactions, so you can just see the algorithm on its own. So I have a graph with some nodes and edges, and I have a new function that's going to create the graph from our input problem. And then I just have some helper functions, add edge, right, as I add an edge to the graph. And obviously I need to insert the nodes, and then I need to add those edges to my graph. This will be again, it's an undirected graph, so I need to add them in both directions, right? The weight of the connection between S and T is the same as the connection between T, and S, right? It's undirected. So for my graph, I'm adding it in both directions. And then if I want to get the edges of a graph, I just need to, right, search through all the edges and find the one that is find all the edges that are associated with that node. I can return a list of, what they connect to and what their weight is. Update edge, when I'm doing the algorithm, when I'm doing the algorithm for the priority queue and I'm like updating nodes, you notice how we're like constantly updating edges throughout it. That's just that's essentially what that does, right? So if you tell me to update S and T with a new weight, I'll update that weight, right? And if it doesn't exist, it's essentially just adding that weight to the thing. But if it does, it's incrementing that weight, right? So when you were in here, like for example, when we moved A into E, there was it'll probably look better here, right? When we were moving A into E, like this weight and this weight were added together, so the new weight, like we removed this one and this one and this one, and so this weight became a 4 because we wanted to add these two weights together. That's what this update edge does. And then obviously once we're done working on A, we want to be able to remove that node from it, and so that's just what that does, right? We remove it from the nodes and the edges, and then we just need to go through all the edges and remove it from any, again, because it's undirected, so we can go in both directions. I also need to go find it in all of the other nodes and remove it as well. And so that's what this function does right here. So given that, we let's talk about that minimum cut phase, right? So that's just this function, the minimum cut phase. And again, the idea is that they mention is to use a priority queue to do it, to do this, like find the most tightly connected. So that's what we do, right? Is we create a priority queue and we add all of the elements or all of the nodes in the graph to it with a default priority of 0. And then we just want to track our S and T values and the cut weight, right? Those are during the algorithm, these are the values that I was tracking over here, right? So we want to keep track of those values. And eventually the last one will have the total weight. So then we're just going to go through the queue, right? We're going to update our values with the new node information, right? We'll have a new S and a new T based on the previous T and the new node in question. And then the weight will be updated with that new node's weight, right? The new one that's coming in. Then we just want to go through, get all the edges of this node right here in question and update the priority of those, right? And that's just a cur plus equals weight, right? So we're going to go through the graph and update weights. Again, this is like the idea is if we're working on if we've already seen F because we've added it to 2 here, F has a value or a priority of 2, but then we come this way from E, right? We want to update the weight here, so F's new priority should be 5. And so it will be picked next over this 3, if you remember how we were doing it. And the reason for that is because its new updated priority is 5. And so that's all we're doing here. And we just do that over and over again until we've popped all the items off the queue. And then when we're done, we return our S, T, and cut weight values. And that is the minimum cut phase. It's actually not a lot of code, right? You can see most of its comments. I added this verbose thing. We'll look at it in a second so you can see what it looks like in the test graph. Obviously, this is a lot of printing for like the real input, but I added these verbosity things in here. You can see it's literally just add all of the nodes to the priority queue, track our state, and then just go through the whole queue until we've added all the edges, updated all the edges, gone through all the nodes, and then the last one that we did is the value you return. There's actually not much to it, right? It was a lot of explaining, and I explained it because I want you to understand the intuition behind it. But once you get to the actual code, there's not much to it, right? So then what is the Stoer-Wagner actual algorithm? The minimum cut algorithm says you basically do that cut phase until you only have one node left in the graph. And once there's only one node left in the graph, you're done. And what are you tracking down here? Like this part right here, you're tracking that lightest phase, right? So that's what we're going to do for the first part, right? First, we're going to make a copy of the graph. Obviously, I mean, I suppose we could say, hey, we're modifying your own graph, but we're going to make a copy of the graph so that we can do those node contractions. And then we just want to track what the best phase was, what the cut value of that best phase was, and any contractions we've done, right? So again, this is when you're doing the minimum cut phase, you're adding each of these values is the way to think about it to these things right here. Okay, and again, it says we do it till we only have one node. So what is that? We're just going to do it from 0 to graph len nodes -1, right? So this is essentially saying we're going to do all but one contraction of the whole graph, right? And that will get us down to everything. And then we just call that minimum cut function, and we just want to update our best phase, right? So if we ever get a cut weight that's best than our current cut value, I could probably rename that. So it wouldn't be cut value. We should say it's best cut weight. They may call it cut value in the thing, and maybe that's why I named it that way. Cut of the phase. They actually call it cut of the phase. So maybe I could go in and rename those, but that's what you get. That's the idea again here is you're saying, hey, what's the best phase I've seen so far, and I need to track that phase. Then I just add my S and T to my contractions, right? This is what I want to contract, and then I actually do the node contraction, right? So I get all the edges that are linked to T, and I update S to contain those things, right? So I call this update edge and so S, all of the ones that are connected to T are now connected to S, and then I can remove T from the graph. And again, just to reiterate, the idea here is if you're contracting A into E, I want to like add all of A's nodes to all of the ones that are attached to A into E, right? So that's B in this case. And so I want to update this edge value to 4. And then once I'm done, I want to remove all references to A, right? And so that's what these two chunks of code are doing. And that's the algorithm. You can see there's not much to it actually, right? Is like if you remove all the comments and stuff, you're basically just doing a for loop, calling the minimum cut phase, updating your best phase, and then updating your contraction list, and then going through and doing the actual contraction, which is, again, just a few more lines of code. So you've done that through the whole graph. That's nice. We don't have a list of contractions, right? So in the original paper, if you look at the paper, they were actually tracking all of them as they go through it, right? They say, oh, the first cut of the phase is partition 1 and then 2 through 8. And so they're actually tracking the partitions as the way through. And this is where I said is like tracking all of them for a really large graph may not be efficient. I don't know. It might be worth trying, seeing which of the two is faster. But the idea is there's like instead of doing it this way, if you're just tracking all of the nodes, all of the contractions, you can then build a graph from it. And that's what we do down here, right? So you can see we go through the transaction list up to the best phase, and we add them all into that contraction list. And then once we do that breadth first search, and any item that we visited in the BFS will be the list of the partition, right? So that's the work I kind of did down here, right? Even though we contracted EA, it's not connected to these contractions that happen down here. And so these ones end up being in the partition when you're doing that breadth first search. These ones do not, right? And so once you've done that, though, you do that BFS, then the visited nodes are the ones that are the quote unquote partition. And so you can just return those values as the solution. And that's the algorithm. So given that, let's run it, and I'll kind of show you what's going on here. So I tried to print these out to give you an idea of like the queue and which ones it picks. And you can see like this is for the test graph. So this one right here. If I try and clean this up a little bit. Just to kind of show you what it looks like. It thinks the first phase should be a GH. So again, combine these two, and the value is 7, and that probably makes sense because the way it did it, it would be 1, 2, 3, 4, 5. Oh no, it would be 2. No, why is it 7? Oh no, it's a 5 because it's 2 and then 3. It'd be these two. It thinks those two would cause G and H to contract, right? But now once you've done that contraction, you then get a 7, a 7, a 4. Again, you've slowly, it looks like you, in this one, CD, DG, in this actual case, it looks like it worked similar to the example that we were doing, where in each phase it was contracting this side of the graph until it got to like a single node where you contracted, what was the last one? It was actually, yeah, F and C, you contracted here again, and the value was 4, right? So you, and notice it does it over and over, and then it says, oh, the best phase was 3, which is 0, 1, 2, 3, 4. So this was the best phase. And so the cut is 4, and then these are the contractions we performed. If we do a graph of, if we create that graph, the partition we get is this to get to the answer, right? And so there you go. That's how Stoer-Wagner works. In the example, you can see it actually running in the code. If I actually run my Stoer-Wagner version, you see I do get the correct answer. It takes 4 seconds to run, but it says, hey, the minimum cut is 3, and here's the value. And the Rustworks does it slightly faster, about a second faster. This is the Rustworks implementation. Maybe they have a faster way of doing that final solution, right, is creating the graph and then doing a BFS. I also return a lot of vectors where I could potentially return an iterator, and that might be faster than like allocating the memory for the vector. So maybe they are doing some things to like simplify that process. They could also have a better, I haven't looked at a lot of it. They could potentially have a better implementation of a graph, right? Mine is a hash map of a hash map, and I'm updating both sides, right? Because it's an undirected graph. If you knew it was an undirected graph, you could potentially do some things to speed that up maybe. And so it's quite possible that they're using like a better version of a graph than I'm using, and that's why theirs is faster. If I run the optimized version of it though, you can see it's pretty fast, right? 339 milliseconds versus 175. Again, theirs is like, substantially faster than mine is the way to say about it. Some high performance increase between 20 and 50%. So there's definitely ways to like make mine faster, but I hope this has given you an idea of how Stoer-Wagner works. And so just in closing, I'd like to say, give the paper a try, look it out, read through it, see if you can understand it. And hopefully you understand the intuition behind it, right? Again, these 3 connections right here are like less tightly connected than all of these over here. And so you're slowly going to contract this side and this side until eventually one of these sides is completely contracted, and that will cause this cut to happen. And this contraction, and this contraction right here will be the minimum of those contractions that happened before. Really cool algorithm. And again, I should say ours aren't weighted, so we just start with a default weight of 1, and that helps solve it. You could potentially use any weight as long as they all have equal weight, then it should find that value, right? but Stoyer is meant to run on any weighted undirected graph, and so the example they give and the one we worked on has different weights, right, to it. But if it's unweighted and undirected, you can make it weighted just by having a default weight of 1, and that's how we solve day 25. Okay, that was a lot of talk. I hope, though, you have a better understanding of how Stoer-Wagner works. Maybe you can go implement it yourself in the language that you're using. But now you have that in your, like, quote unquote toolkit for when another problem like this comes up. You can say, oh, I've seen something like this before. It looks similar. I can use Stoer-Wagner to solve it. And there you go. So I think the next video, I'm not sure what I'm going to do. I have a bunch of ideas. Obviously, if you have any ideas, I'd love to see what you're interested in, and I can talk about those too if our interests are aligned. Interests are aligned. Okay, apparently I've been talking too much because now I don't remember how to talk. But I'd be happy to work on things that you want to work on. Otherwise, I'll just keep working on my list and share my information. Again, one of those that I think would be interesting is if you look at RustWorks Core and compare it to, like, Network X. It's missing some of the things that I haven't seen in Network X. For example, like, it's got the Bellman forward for the shortest path, but it doesn't have the forward Fulkerson for the max flow, which is another way to solve. If you remember the way we solved it in Python, the other way to do it was to do the minimum cut, run minimum cut using the max flow to get to the solution. And what you did was you just said, oh, I'm just going to iterate through all the nodes and see what the minimum cut is between those two nodes. And if I ever get one that's 3, I know that I've found the answer to the problem. We could try and implement this in Rust and maybe even give it back to the RustWorks Core people. Or I haven't looked too deeply. Maybe they do have it and I've just missed it. That's a potentially cool next video that I'm thinking about doing. But again, the field's open. I hope you've enjoyed Advent of Code for the year 2023. I plan to keep doing this, and I plan to do 2024 as well. But in the between time, yeah, hopefully we can find some more fun stuff to talk about and keep the community growing and learning, right? Like, that's the goal. Is I learn a lot from this. Hopefully you all learn a lot from this, and communicating together via the comments and other ways are a good place for us to, like, grow and learn together and just become better programmers, better computer scientists, right? Imagine going to work and saying, oh, did you guys read the article from 1995 about the min-cut algorithm by Stoyer and Wagner? I'm just kidding. Don't do that. You'll look weird, right? But reading this stuff, I think, is really cool and can help you become a better programmer because it makes you start to think like some of those really good programmers. So give it a try. See if you can read it, and if I'd be interested in your insights about the paper as well. So feel free to leave that stuff in the comments. And with that, I will say goodbye, and we'll talk to you in the next video.